Okay, so let's solve another example. This one is a little bit more complicated circuit, but the principles that we're going to use are pretty much the same. So here we have independent sources, dependent sources, and the question is pretty much the same question. So using Ohm's law, KCL, KVL, we want to find this voltage across the current source with the polarity that is shown and the current that is passing through the 54K resistor. Okay. Uh, Also, the second part of the question is asking us to check the power balance. We know what does that mean, so we're going to do that as the second part of the question. So I'm going to ask you guys to pause the video right now, try to do it yourself, and then once you're done, you can resume the video and then we'll solve it together. Okay, so the first stage, the first step in solving this question or in analyzing the circuit is to actually define the current through this branch. I'm going to define it as I2 because, well, I have two currents coming into the node, I1 here and 30 I1 here. So I can imagine that, well, it makes sense that the current is going out. That's why I draw the direction from top to bottom. Okay, I'm going to start by writing the KCL at node A. The KCL is telling me that I1 plus 30 I1, the two currents that are coming into the node, are equal to the current that is going out of the node, which is I2. Therefore, I can say that I2 is equal to 31 I1. Next, I need to actually relate I1 and I2 with another equation so that I have a two equation, two unknown to solve it, right? So I'm going to use this path. Basically starting from here, going around this closed path, and I'm going to write the KVL. So the KVL in that path, if I want to write it, is going to be plus 5 minus 54 kilo ohm times I1 plus 1 volt minus 6 kilo ohm times I2 is equal to 0, right? So if I want to simplify that, I'm going to have 6 minus 54 kilo ohm I1 minus 6 kilo ohm, and then instead of I2 I'm going to write 31 I1 because, well, from the top equation I have that is equal to 0. So 6 is going to be equal to 6 minus 54k I1 minus 186k I1 is equal to 0. Therefore 240k I1 is equal to 6 volts. Therefore I1 is equal to, if you do the math, you'll find 25 microamp. Okay, so that's a good math practice for you guys as well. Make sure that you actually get that number. Okay, now I got the I1, which is one of the parameters that I was looking for. Now the next thing that I will need to find is V here, right? So to find that, I need to actually write an equation that, well, somehow relates, that somehow includes V, and then I'm hoping that I can somehow relate it to I1 and I2, basically the parameters that I know their value. So this time I'm going to write a KVL along this path, and you can see that this time the KVL is actually, the way I'm moving is actually counterclockwise. So that should tell you that it doesn't really matter which direction do you move. Basically, the important thing is that it's a closed path and you basically follow one of the conventions for writing KVL as we have discussed before. So here, if I want to write this KVL, I'm going to get plus 8 volts minus 1.8 times the current of this path. So what is the current here? The current that is passing through the resistor, the 1.8 kilo ohm resistor. If you think about it, this resistor is in the same branch that the current source, the dependent current source, exists. And I know that the current of the current source is actually posted on it. It's 30 I1, right? So the current of the resistor is going to be 30 I1. So this is just going to be 30 I1, right? And then I get to the current source. I need to write the voltage. Remember, this is one of the most common mistakes. Not a lot of you do it, but it's very annoying because it does not mean anything. So when you're writing KVL, each of these terms that we are writing is a voltage, right? So here's an 8 volt, right? The voltage, this term is the voltage across the resistor. It's an RI. So it's very common during the exam, you're stressed out, and then you reach to a source and then you see, oh, 30 I1, and you just write 30 I1. but that's the current of that current source. We're looking for the voltage. We have to write the voltage term because it's KVL, it's Kirchhoff's voltage law, right? So what is the voltage across this current source? Well, V, basically the unknown that we're looking for. Since we're going up in terms of potential based on the polarity that is defined there, I'm just going to write plus V. And then we get to the 6 kilo ohm. So minus 6 kilo ohm times I2 is equal to 0. Now, again, I'm going to simplify this. 8 volts minus 1.8 times 30 is going to be basically 54. So, by the way, this is kilo again. So 1.8 kilo, sorry, 54 kilo ohm times I1 plus V minus, now 6 kilo ohm times I2. I2 is 31 I1, so this becomes again 186 kilo I1 is equal to 0. Therefore, 8 volts minus 240 kilo I1 is equal to negative V. Therefore, 8 volts minus 240 times 10 to the power of 3, and I1 is 25 microamps, so times 10, 25 times 10 to the negative 6 is equal to negative V, right? Now, if you simplify this, you're going to get to V being equal to negative 2 volts. Okay, so we got I1 and we got V, and we're pretty much done with the first part of the question. So for the second part of the question, the question is asking us to check the power balance, right? Again, if you haven't done it, try to pause the video at this point and do the power balancing check for yourself, and then we'll resume the video and then we'll solve everything together. Just to give you a hint, to do the power balance, you need to calculate the VI of each component, but then remember those 4 different types that we had for power calculation. Sometimes, so when we had an element with the polarity plus, minus, and the current was going into the element at the plus sign, P was equal to VI. We call this case A. And then if we had another element and the current was actually coming out of the plus sign, we said P is equal to negative VI, right? So as long as you follow these instructions, because if you remember we said we have 4 cases, but in reality there are 2, right? So if you can actually tell for each element which one of these cases we are talking about, then is it a case A or case B, you should be able to write the power equations. Okay, so I'm going to pause here. I'm going to ask you to pause here and then do it for yourself, and then we'll do it together. Okay, so let's do this together. One thing that you should have figured out by now is that for a resistor, we know that P is equal to VI, right? And then, but then the nice thing about the resistor is that the V and I of a resistor are actually related to each other, unlike other components, unlike the voltage sources and current sources, that their voltage and current have no relationship with each other. For a resistor, we have Ohm's law. So instead of V, I can write Ri, and then if I keep the I, this is going to be Ri squared. Okay, and then for an similarly, I could have replaced I with a V divided by R, so this could have been V squared divided by R. Okay, so power of a resistor is basically Ri squared or V squared divided by R. So depending on if you have the current or voltage of a resistor, you don't have to calculate the other one. You can just by having the resistance and one of the current or voltages, you can calculate the power. The other nice thing about these two is that you can see that since R is always a positive value, we don't have a negative resistance, we always have positive resistance, and I squared and V squared, no matter what is the polarity of I and V, or the sign of I and V, their square is always positive. You can see that why power of a resistor is always positive, why a resistor is always consuming power, right? So for resistors, we don't really need to actually tell if it's a case A or if it's a case B, right? it's always positive. It's always, you don't really need to even think about it. Okay, so because of that, let's actually start with the resistors. So for the 54K, power is 54,000 times I squared, which is I1 squared. So it's going to be 54 times 10 to the power of 3 times 25 times 10 to the negative 6 to the power of 2. If you do the math, you will find basically the power to be 33.75 microwatt. Great. Next, we're going to talk about the 6K. So for the 6 kilo ohm, again, P is equal to Ri squared, so 6,000 times I2 squared, and I2 being basically 31 I1, so 775 microamp. We're going to have 6 times 10 to the power of 3 times 775 times 10 to the negative 6 squared. So you're going to get the power of 3,603.75 microwatt. By now you might wonder that if you're allowed to have a calculator on the exam. Of course you do. Well, a simple calculator, not a programmable one, but you can imagine that yes, you are allowed to have that. Then the 1.8 kilo ohm, again, power is going to be Ri squared. So R being 1800, 1800, and the current is going to be 30 I1, so 750 microamp. So 750 times 10 to the negative 6 squared. If you do the math, you will get 1012.5 microwatt. So these three were extremely simple, just the simplest math possible. Now the next three are going to be the next four are going to be the voltage sources. We're going to start with the independent sources, and then we're going to continue to the dependent sources. So let's talk about the 5 volts. So the 5 volt source, P is equal to VI. Well, is it VI or negative VI? Let's look at it. The current of the 5 volt is actually in this direction, right? Because it's I1. That's the current that we have decided to have for this one, right? So I1 is passing through 54K, so it is passing through in the same direction passing through the 5 volt source. So looking at it, I can see that the current is actually coming from out of the positive terminal. So since this is out of the positive terminal, therefore it's case B. See, current is coming out of the positive terminal. Therefore, I can say that P is actually equal to negative VI. If I write it down, V is actually 5, and I is the 25 microamp. So 25 times 10 to the negative 6. So the power is going to be negative 125 microwatt. Good. Next is the 1 volt. So for the 1 volt, again, I can see that the power, the current is actually in this direction, so it's coming out of the positive terminal. Therefore, I can say P again is equal to negative VI. So it's going to be negative 1 times, the current is the same, so 25 times 10 to the negative 6. So it's going to be just 25 microwatt, negative 25 microwatt. Okay. Next is the 8 volt. So the 8 volt source, again, I can see that the current is actually coming out of the positive terminal. Again, I have P equal to negative VI. So it's going to be negative 8 times, and the current is 30 I1, so 30 times 25, that's 750 microamp. So it's going to be negative 6,000 microwatt. And now we have just one last element, which is the dependent current source. So I'm just going to call it dependent source. So for that, I can see that again, the current, which is in the direction of from right to left, is coming out of the positive terminal. So P is going to be negative VI. So here I want you guys to pay attention because it's actually quite interesting. So you can see that, well, I'm going to put the negative, but now what is V? V itself is a negative value, so it's going to be another negative 2 here. And then I is, well, 30 I1, so it's similar to the previous one, so 750 microamp. Doing the math, I'm going to get a positive value for here, so 1500 microwatt. Okay, let's see if we have a balance. So 3603 plus 33 plus 1000 plus this. So basically, so this is a positive number. So is this one, and this one. And then the negative ones are, let's show them with light green, this, and this. So basically the negative ones are easier to actually add up. It's basically 6,150 microwatt. These are the powers that are generated. And if you do the math, you will see that you're going to get exactly the same power if you add up the positive numbers. So the positive numbers are going to be 6,150 microwatts consumed. So yes, we do have power balance. Okay, I hope everything was clear.